there! Welcome to Lab Partner 101, your study buddy for making science and math simple. I'll walk you through tough concepts step by step so you never feel lost. Let's dive in. Welcome back to Lab Partner 101. Today we're exploring one of the greatest scientific tools ever created, the periodic table of elements. It's more than just a chart on the wall. It's a roadmap of matter itself, showing us how atoms behave, why elements interact, and even predicting discoveries before they happen. Let's start with a quick history lesson. In the early 1800s, John Dalton, around 1803, introduced the idea that matter is made of indivisible particles called atoms. In 1897, J.J. Thomson discovered electrons. Just over a decade later, in 1911, Ernest Rutherford uncovered the nucleus. In 1913, Niels Bohr proposed energy levels where electrons orbit. Then, through the 1920s and 1930s, quantum mechanics refined this picture, showing us that electrons exist in clouds and orbitals, not the neat little circles often shown in textbooks. Each of these discoveries brought us closer to understanding how the periodic table organizes the building blocks of matter. The first real periodic table came in 1869, when Dmitri Mendeleev arranged the 63 known elements by atomic mass. He noticed repeating patterns in their properties, what we now call periodicity. His boldest move was leaving gaps, predicting elements that hadn't yet been discovered. In the 1870s and 1880s, discoveries of gallium, scandium, and germanium fit perfectly into those gaps, proving Mendeleev's genius. Later, scientists realized that atomic number, the number of protons, was the true organizing principle. This shift, led by Henry Moseley's work in 1913, replaced atomic mass with atomic number and gave us the modern periodic table. Before we go deeper into electron shells, let's zoom in on the atom itself. At the center is the nucleus, packed with protons and neutrons. Protons carry a positive charge, neutrons are neutral, and together they account for nearly all of an atom's mass. Orbiting around the nucleus are electrons, tiny, negatively charged particles. They're incredibly small compared to protons and neutrons. In fact, if a proton were the size of a baseball, the electron would be smaller than a grain of salt. Yet moving so fast, it's essentially a blur. Electrons are held to the nucleus by the positive charge of protons. But they don't just stick to the nucleus. They occupy specific regions called shells or orbitals. Electrons move at incredible speeds, a significant fraction of the speed of light, which is why we describe them as forming clouds rather than neat planetary orbits. The first shell can hold up to 2 electrons, the second up to 8, the third up to 18, and higher shells can hold even more. For the first 20 elements, the ones you'll usually encounter first, the third shell typically fills with just 8 electrons before the fourth shell begins to take electrons. That's where the famous octet rule comes from. Atoms are most stable when they have 8 electrons in their outermost shell. It's a simplified model, but it's extremely useful for predicting the bonding behavior of many common elements. The periodic table is also divided into 4 major blocks, named after the type of orbital where the outermost electrons are found. S block. This is the far left side of the table, groups 1 and 2 plus helium. Elements here have their outermost electrons in an s orbital. These are the alkali metals and alkaline earth metals, which are highly reactive. P block. On the far right side, groups 13 through 18. Here, the outermost electrons are filling p orbitals. This block contains a huge variety of elements, from nonmetals like oxygen, nitrogen, and fluorine, to metalloids like boron, and even some metals like lead and aluminum. D block. In the middle, groups 3 through 12, you'll find the transition metals. Their outermost electrons go into d orbitals, which is why these elements often have multiple oxidation states and form colorful compounds. F block. At the bottom are the lanthanides and actinides. These elements are filling f orbitals, and many are rare or radioactive. This block structure isn't just a way to organize the chart. It reflects how electrons fill orbitals in a predictable order, which is the foundation for electron configurations. Let's connect that idea. Electrons fill orbitals in a specific order. The 1s orbital fills first, then 2s, then 2p, and so on. The arrangement of electrons is called an electron configuration, and it explains nearly every chemical behavior. Oxygen, with a configuration of 1s2, 2s2, 2p4, has 6 valence electrons, so it needs 2 more for a stable octet. Sodium, with 1 lonely valence electron in its 3s orbital, is eager to give it away. This is why sodium reacts violently with water. It hands off its electron, forming sodium hydroxide and releasing hydrogen gas and energy. Atoms of a given element always have the same number of protons, but the number of neutrons can vary. These variations are called isotopes. For example, carbon-12 and carbon-14 are both carbon, but with different masses. Isotopes come down to the balance between protons and neutrons in the nucleus. Protons are positively charged and naturally repel each other. Neutrons help hold the nucleus together by providing a stabilizing force without adding more repulsion. In carbon-12, there are 6 protons and 6 neutrons, a perfectly balanced ratio that makes the nucleus very stable. In carbon-14, there are 6 protons but 8 neutrons. That extra weight tips the balance just enough to make the nucleus unstable. Over time, carbon-14 undergoes radioactive decay, releasing energy and transforming into a more stable atom. This instability is why carbon-14 can be used for radiocarbon dating. It decays at a predictable rate with a half-life of about 5,700 years. Stable isotopes like carbon-12 don't decay at all, which is why they make up the vast majority of natural carbon. Isotopes aren't just a curiosity of nature. They're essential in science and medicine. For example, iodine-131, a radioactive isotope, is used to diagnose and treat thyroid conditions. And because elements exist as mixtures of isotopes, the atomic mass listed on the periodic table is usually a weighted average, not a neat whole number. Before we dive into the trends, it's worth mentioning atomic symbols, the shorthand of chemistry. Each element is represented by 1 or 2 letters. For example, H for hydrogen, O for oxygen, Na for sodium, from its Latin name natrium, and Au for gold, from aurum. These symbols are universal, letting scientists around the world communicate about elements without confusion. The periodic table isn't just structure, it encodes trends. These periodic trends are the real power of the table. Let's start with atomic radius. Basically, how big an atom is. As you move down a group on the periodic table, atoms get larger. That's because each step down adds a new electron shell, increasing the distance between the outermost electrons and the nucleus. For example, lithium at the top of group 1 is much smaller than cesium at the bottom, which has 6 more shells stacked around its nucleus. But as you move across a period from left to right, the trend flips. Even though atoms are adding more protons and electrons, the new electrons are going into the same shell. The stronger positive charge in the nucleus pulls the electrons in more tightly, so the atoms actually shrink. For instance, sodium is noticeably larger than chlorine, even though chlorine has more protons and neutrons. The greater nuclear charge of chlorine makes it more compact. Second, ionization energy. The energy needed to remove an electron. It decreases as you go down a group and increases as you go across a period. That's why metals on the left lose electrons easily, while nonmetals on the right hold on tightly. Third, electronegativity. An atom's pull on shared electrons in a bond. Fluorine, in the top right, is the most electronegative element. It practically drags electrons toward itself. Fourth, electron affinity. How much energy is released when an atom gains an electron? This also increases across a period. Finally, metallic character. As you move left and down, elements become more metallic, shiny, malleable, conductive. As you move right and up, they become more non-metallic, brittle, insulating, and chemically reactive in different ways. Now let's highlight some families. Group 1, the alkali metals like lithium, sodium, and potassium are highly reactive. They have 1 valence electron and will do almost anything to get rid of it. Group 2, the alkaline earth metals are also reactive, though less violently. The transition metals in the middle, like iron, copper, and gold, are versatile, forming colorful compounds and essential to industry. On the right, Group 17, the halogens, are aggressive nonmetals. Fluorine, chlorine, bromine, and iodine are highly reactive because they need just 1 electron to complete their octet. They form salts when paired with metals like sodium chloride, table salt. Group 18, the noble gases, are the opposite. Helium, neon, argon, and others have full valence shells. They're so stable they barely react, making them perfect for lighting, balloons, and inert environments in labs. Don't forget the bottom rows. The lanthanides are used in strong magnets, lasers, and electronics, while the actinides include radioactive elements like uranium and plutonium, central to nuclear power and weapons. So let's step back. The periodic table is more than a list of elements. It's a story of scientific discovery, a system for predicting behavior, and a foundation for chemistry. Its rows and columns tell us about electron structure, its trends reveal patterns in reactivity, and its families show us why matter behaves the way it does. In our next lesson, we'll build on this by looking at how atoms use their valence electrons to form chemical bonds, the glue that holds matter together. That wraps up today's lesson here on Lab Partner 101. Thanks for exploring the science with me. If you found this video helpful, don't forget to like it and share it with a friend who's curious about chemistry. And if you want to keep learning, hit subscribe so you don't miss the next deep dive where we'll explore how atoms form bonds, the glue that holds matter together. Until next time, keep asking questions, keep experimenting, and stay curious.